Hi, SREcon. My name is Marianne Bellotti, and this is my cat, Smokey Jones. And I'm going to talk today about system dynamics and bringing system dynamics back to computer science. So, a little bit about me to get started. First of all, again, my name is Marianne Bellotti. You can find me on Twitter and Medium and most social networks under the handle Belmar. I've spent about 15 years as a software engineer. I just wrote this book called Kill It With Fire, which focuses on the period of my career where I was really working on legacy modernization and the things that I learned from that experience. Nowadays, I tend to focus more on hybrid intelligence than defense and national security industry. Basically, what I'm saying is I'm a lover of complex systems and failure on complex systems. And I specifically spent about 3 to 4 years doing rescue on critical systems as part of the United States Digital Service. So systems that when they fail, it's more than bad publicity on the tech blogs. It's like people get hurt and economies get negatively affected. So as a result of this work, I got really interested in how we think about systems, and specifically kind of went deep into an independent study around this school of thought called system dynamics. And what's important to know about system dynamics is that system dynamics is essentially a methodology for modeling systems. You want to model systems as a way of expressing complex systems, because most complex systems, you can't fully communicate what they are doing to another person unless you are able to sort of visualize them and break down and compartmentalize and abstract them in some way. So this is a method for doing that. And there are lots of different methods for modeling systems, some of which we're probably familiar in computer science and some of which are very foreign to us. A lot of the approaches that we use in computer science around modeling systems kind of focus on logic-based rules, whereas system dynamics focus on this concept of feedback loops, reinforcing feedback loops, diminishing feedback loops, and how various parts of the model affect other parts of the model and change behavior over time. It's extremely popular in policy circles, which is interesting because it actually originated at MIT with a pool of mathematicians and really early computer scientists. So the fact that it doesn't really exist within computer science anymore, but it has found its home within policy, is to me a really interesting challenge for us moving forward. Like, can we make use of this? So what's interesting about the development of system dynamics is it really has its origin in a movement at MIT around the 30s and 40s called cybernetics. And cybernetics emerged at a time when physics had spent like several decades making huge progress in defining rules that govern the natural world. And so that naturally led to the question of, are there similar and comparable rules for how organizations work, for how societies work, for how cognition works? Like, can we find the equivalent of general relativity for human behavior and social behavior? And so I'm not going to go into cybernetics because I've actually done a fair amount of writing about the history of cybernetics. You can find on my blog, there's one particular post called A Software Engineer's Guide to Cybernetics that kind of goes into more detail if you're interested. But the important thing to understand about cybernetics is that the people who are involved in that movement are the founders and forefathers of computer science. They established chip architecture, they pioneered concepts around neural networks, and they were very highly influential, not just in the design of computers, but also in networks and what eventually became the internet. One of the personalities that was involved in this scene is a man by the name of J. Wright Forrester, who might sound familiar to you because, again, like titan of computer science, heavily influential, and particularly in the development of magnetic core memory and what eventually became RAM. So lots and lots of accolades on the computer science side of things. And around the 1956, he basically decided there are no hard problems left in computer science. Everything has been solved, which is somewhat funny from a modern day perspective. And he was no longer finding the really challenges that he wanted to get out of computer science. So he decided to move over to the very recently founded business school in MIT and started working on this concept he called system dynamics. And it essentially is a control theory for economics. And so how that came about is that he had a contract with GE. They came up to him and they said, we keep having this problem where we either have too much inventory or too little inventory. And so their expectation was this great computer scientist was going to build them a computer or a computer program that was going to look at their inventory at any one period of time and know exactly whether they should be getting more or slowing things down and to get rid of extra inventory. And that's actually not what he did. When he looked at their problem, he started studying their processes and what was going on. He saw something that he had seen when he was involved in the war effort, which was that when they take a shot from a Navy vessel and it misses, the next shot also misses, but it tends to be a massive overcorrection based on the first shot. And that actually what people were doing is that they were overcorrecting one way and the other, like a pendulum, until finally they got to about where they were supposed to end up. And this was the kind of domain of control theory, right? And so what they ended up doing when they were building out systems to target more effectively is they learned to factor in environmental forces and respond to the change in the environment around them when they were approaching these calculations, right? So you could either had counteracting forces that could limit and restrict changes, or you had intensifying forces that could amplify your change. And the control theory became really pivotal in not just targeting systems, but also steering ships and all sorts of different applications. And so it was this question of we need something like the equivalent of control theory for these processes. But the disadvantage we have here is that we can't really measure the processes, every little environmental factor of the processes. So we kind of have to take something of a more nuanced approach. And so he developed this way of modeling that involved two primary abstractions: stocks, which were pools of resources, and then flows, which were rates of change upon those resources. And so the classic example when people start learning about system dynamics is the bathtub full of water. You have the water flowing out of the faucet, which is a flow. You have the water flowing out of the tub into the drain, which is another flow. The bathtub itself is a stock. So these are the primary abstractions that govern system dynamics. So let's go back for a second to modeling in software, right? So the early computer science developed huge benefits from thinking about systems in this fashion and researching systems in this fashion, but this is not how we think about systems today, really. And the way we model systems today in computer science is either purely anecdotal. So we do things like threat modeling that are just designed as thought experiments to get us thinking about systems, or we do them in a very structured, formal way, like formal methods that are focused primarily on mathematical correctness of our systems. So you may be familiar with things like Coq for writing proofs, TLA+, or Alloy. These are all very popular languages for modeling systems in computer science. And the problem with mathematical correctness is that it focuses on impossible states. Essentially what you're doing, you're modeling a system in a formal methods approach, is you're trying to figure out what states are impossible and then building a model that proves that those states are in fact impossible. And when you're doing things like testing algorithms, that makes a lot of sense and that works really well. But when you're doing things talking about distributed systems like cloud-based systems, it starts to break down a lot because distributed systems don't fail due to impossible states, they fail due to undesirable states. If my load balancer kills the server, that may trigger an outage, but I would not describe that as an impossible state. I want the load balancer to be able to do that. It's good that the load balancer is able to do that. And so what we're really seeing when we're talking about distributed systems and failure on these kind of large, complicated distributed systems that we all run is a set of feedback loops that are creating a context that triggers unexpected behavior, not impossible behavior. And so here's an example. Who remembers when AWSkinesis basically took down the entire internet in 2019. It was a huge outage. And if you read the postmortem report, what you would understand about this outage is that what happened is that they had their front end and their back end running on servers, and they weren't factoring in the capacity of the operating system of the instances into how they configure the front end and the back end. So the front end did two things. It routed requests to the right back end, but it also built a map and maintained a map to speed that up. And so when they changed the configuration of the front end so that it was increasing the amount of memory that it was using, it actually overloaded the operating system capacity. And this did two things. One, it took down the front end, but it also corrupted the map. So it triggered a huge outage that affected, you know, when something on AWS goes down, it affects basically the entire internet goes down as a result, right? And so when we're talking about problems like this, could we have found this problem using the modeling tools that we use in computer science today? And like in theory, we could probably write a proof that shows that the front end can exhaust the capacity of the operating system. But in practice, we would never think to build such a model because we would never see the operating system in scope with the same scope as the model that we designed the software around. Because the real problem here really isn't what the software is doing or what the operating system is doing. It's the feedback between those two things, right? And the coupling between them. So I know that this audience doesn't need to be told this, but these type of outages happen a lot, right? These are just like 6 months in the same year as the Kinesis outage. It happened twice to Twitter, twice to Facebook, Microsoft, Google, Verizon, Comcast went down, Slack went down, Apple went down. Like these are companies that are not bad at building and maintaining systems. It's just these systems reach a level of complexity and coupling that makes it very, very difficult to control like the blast radius of outages when things start to go wrong. And so when we deal with systems of systems, the largest cause of failures on these like large systems is configuration change, which just basically means a little change here led to a huge cascading out of control outage somewhere else. But the reality of it is that we don't trigger these outages because we don't test our code or we don't test configuration changes. It's just that within the small subsystem in which that configuration change happens, it tends to be stable. The small subsystem doesn't demonstrate the problem that might happen. But our modern computer systems, especially in production environments, chain several systems together and create feedback loops between them. So when we have tight coupling in various parts of these systems, it becomes extremely difficult to stop failure from cascading all through the system. And it also becomes extremely difficult to anticipate what failure might happen. So we'll come back to this idea of mathematical correctness. It's great to be able to focus on like impossible states, but we really need to also be able to model undesirable states. We need to be able to really be able to demonstrate and model feedback loops and what kind of unexpected behavior they might trigger. And coupling is really, really important. We need to be able to see what the system looks like when it's decoupled in different positions and when it's tightly coupled in different positions. And what's really interesting about stock flow models is that they're really good at expressing coupling, right? When you have multiple changes expressed within a single flow, you're essentially saying that this is a tightly coupled system and it will behave as if it's a tightly coupled system. But when you separate those changes into different flows and put a stock in between them, now the behavior of the system is loosely coupled because that stock kind of forces a delay that allows you to interfere in the chain of events if things go wrong. And so much like threat modeling, system dynamics can sort of help us understand and learn and ultimately reason about systems and the risks of building systems one way versus building them another way. And so let's look at one way we might represent that, taking that Kinesis example. We can look at what's going on between the front end and the operating system as an exchange of memory, right? We're executing certain requests and then we're releasing the memory that we use to execute those requests back to the operating system. And so that might look like something like this. We might use memory as stock And then we might use these tasks as flows, taking memory from a free stock, moving it into a used expended stock, and then recovering it and sending it back, right? This is one way we could model a system like this using a stock flow abstraction. So there's a lot of information. I can only touch the surface of this type of modeling in like a 30-minute block. And so I have some recommendations that I like to direct people when they want to learn more. The place where everybody ultimately seems to start is this wonderful book called Thinking in Systems by Donna Meadows. She's one of the pioneers of the field. This is a book that's not very technical. It's really geared towards policy people, but it's kind of very easy to break down the abstractions and look at different types of systems and different types of feedback loops and try to map them to what you want to model. The second really great resource is that there's actually a System Dynamics Society that has a yearly conference where they present academic papers. They also do regular trainings. They're very excited about getting people from different industries and different methodologies involved in the system dynamic community. So they've got lots of great resources, including models that other people have built, software solutions, all sorts of stuff. And then one of the tools that I think it's very simple and it's sort of a great place to get started and playing around with how systems can look in this fashion is a tool called Loopy. It essentially runs simulations of very simple stock flow models. And so it allows you to sort of play around with exploring how you might think about computer systems in this fashion. And then when you're getting a little bit further on and you're ready to sort of do some modeling, these are sort of the conventional tools that people use. Insight Maker is a web-based tool written in JavaScript, very simple but very sophisticated, that allows you to sort of build stock flow models and then write in the functions the flows follow. Symlin is a relatively new visualization tool that someone sent me a couple weeks ago that I really love because I think visualization is really clean and really elegant. Again, another web-based tool. There's a set of Python libraries that allow you to take conventionally written system dynamic models and actually sort of integrate them with machine learning and more conventional programming approaches that I think is really clever and really interesting. And then like the conventional closed source proprietary modeling tools that most of the system dynamics community uses, PowerSim, Vinson, I think, and Stella are the big names in this. So when people write academic papers and produce a model, generally they're producing it in domain-specific languages for these tools. Which brings me to my pet project in this field, which is I don't like closed source and I'm not a huge fan of proprietary software. And I especially think that we benefit when models can be run and we can reproduce results and actually have intelligent conversations as practitioners. So about a year ago, I started kind of playing around with writing a programming language to express system dynamic models, both to have a tool that reflect what I wanted to do with these models, but also because it seemed like a fun thing to do to write a programming language. So it's really the idea of the Fault project is to create model checking for system dynamic models, because all of the conventional tools right now, they're really based on simulation. So you put in your parameters, you build your model, and it'll run your model and show you what happens, give you graphs of like how stocks deplete or increase, things like that. But you can't really say, okay, but if this state ever occurs in the model, we have a problem. So like, tell me the situation in which this state might happen within this model, which are the advantages of formal methods that we lose out on when we give up on the sort of logic-based programming. So what Fault does is it essentially takes a stock flow relationship and then compiles down to SMT under the hood and runs it like it is a logic-based model. And one of the great things about applying this kind of approach to system dynamic models is when I talk to people who build system dynamic models about like, what's the number one mistake people make when modeling, they'll say things like, well, you don't check to see if your stock can go negative or not, things like that. And I'm like, well, you know, programming languages have all these wonderful abstractions like type systems that allow you to essentially have the language tell you you're not allowed to do that with that data type. And so it allows us to build better, more efficient models. And as I've been doing this project, I've also been doing a podcast about my experiences learning how to build programming languages and system dynamic models applied for computer science and distributed systems. So I've actually been having a wonderful time on this project, and I would very much love it if people would check it out. Okay, so let's see if I can give you a little bit of a demo about what I've been working on with Fault to close this out. Okay, so now that I got everything all set up on my ID, this is basically what Fault looks like so far. I wanted to keep it super simple. I was very heavily inspired by the syntax of Alloy, where you can define flows and you can define stocks, and then you can define what are called run blocks, which basically says a single loop of the model, what's supposed to happen, what are the interactions between these components that you've put in the spec. Like all model checking structures, it's a bounded model, which means that you have to, it's only going to run for a certain number of loops, and then it's going to go, okay, if it's good for this number of loops, I'm going to assume it's good forever, right? That's pretty common with a lot of logic-based models because SAT and SMT are NP complete problems, which means it's entirely possible that your model could just never return a result ever. So we have to keep things bounded to prevent that from happening. And so this particular syntax right here using the pipe is something I've been working on lately to allow flows to actually run concurrently. So instead of modeling it as the water comes into the bathtub and the water goes out of the bathtub, which is what this little basic toy model represents, the water is coming in at the same time the water is coming out. So I wanted to sort of play around with like, how do we actually like implement that? And so what Fault will do is the first thing it will do, and I'm having it print to standard out so I can show you, is that it will take this code, parse it, and then generate LLVM intermediate representation based on it to sort of flatten it out and express how that actual loop of behavior behaves. And then what it'll do is it'll take that representation. Eventually we'll be able to run optimization passes on it, but it'll take that representation and it'll convert it to SMT-lib2, which is the primary language that we use for model checkers like Z3. So that's what this looks like. And if you've ever seen a SMT model before, you know that they're extremely long because you have to essentially define all of the possible states within the model so that it can do its logic wonder and figure out whether or not you can invalidate any of your constraints. What's particularly interesting about this model is that these two processes are running concurrently. So what it is actually doing here is it's kind of creating a branch where, okay, we speculate that the in process finishes before the out process. And so what do the numbers look like when we do that? And then it's doing another scenario where the out process finishes before the in process. And then it's right down here, it's creating a new assertion that the end state either equals the end state from scenario 1 or the end state from scenario 2. And then in the next loop, when it repeats all of that, it uses that end state. If you're familiar with logic, this is basically called a phi. It uses that as the starting point for the next two scenarios and so on and so forth. So all of this just looks like a whole bunch of Polish notation, right? Well, I can actually take this model now and run it in Z3. And to do that, I would do this. And so now Z3 can parse this model. It says, yes, I understand it. There is a solution that fits all the assertions that you've given me, and here's what it looks like. And it defines the conditions of the state of each one of these variables. And what's exciting about this is that now that it's up to this point, now I can actually write in the ability to write assertions. So we can add to this model right here, and we can say like, okay, we assert that the bathtub, so let's say tub level is always greater than, let's add 2 units or something like that. We can write in all kinds of assertions, and Fault will take that logic, parse it, represented in SMT, and then run the model based on that assertion. What I'm hoping to get to is at the point where we can then build these really small subsystem models and then have one model file where we import those small subsystems and actually chain them together and then write a run block that does a much, much larger system. So you can test the small subsystems, and then you can reason about and test the larger combinations of subsystems. All right, so thanks so much for taking the time to listen to my talk today. It's been great fun to sort of explain some of the work that I'm doing now and some of the reasons why this is an interesting field for people in SRE in particular, but computer science in general, to start to learn about and explore and play around about. Again, if you want to reach out to me for more information, you can find me on most social networks under the handle Belmar, and you can find the source code for Fault's pre-alpha on GitHub. And I'd really love to continue the conversation on other forums of channels. So I hope you enjoy the rest of the conference, and I'll hope to see some of you later. Bye.